Let's start our today's class. Good evening, students. Thank you very much for joining the today's session for the preparation. As you may check the Blackboard that I have uploaded the extra assignment for those the low marks in the mid. So the others should also try it. You should also solve it. It's good for you. Of concepts, okay? Uh, yeah, after the deadline. After the deadline. So today's lecture, we will be discussing about the new chapter, which is magnetostatics. Previously, we were discussing about the electrostatics, and we came across different concepts. Here is the comparison and the summary of both the dimensions of the electromagnetics. Remember, there's one thing common, which is the statics part. Uh, I will try to explain what does it mean in terms of electro and magnetostatics. Since the name suggests, the statics means that uh, at rest, right? If you consider the electrostatics, that means that there is no current, right? And you can only have the charges, right? Uh, and the charges, when they are at rest, there is no current. So what we call the static electric field. Okay. So in magnetostatics, we cannot have a rest charges. Otherwise, there is no magnetic field. So in this field, we should have a current, right? That means that the charges, they are moving at a steady speed, right? So technically, that means DC current, right? That means that the current itself is not fluctuating. So current remains constant, right? That's a 5 ampere, 6 ampere, 10 ampere. So that's the DC current. So the source in electrostatics is the charge density, right? So you can have a plate, right? And that have some charge density rho v, okay? And the fields and fluxes are due to the electric field and the field displacement D. Remember, we learned that we learned the relationship between the displacement field and the electric field, right? So we actually analyze that the electric field is due to the charges. So it's a natural phenomena, right? So if you have a charges, then you have electric field. But the behavior of that field is different in different materials, right? So how the material and its construction and its natural constellation helps us to get the impact of electric field is what we call the field density. In order to understand that, we have to look at the epsilon, which is permittivity, right? So we learned that the permittivity is the property of the material, that how much it allows the electric field to get passed through it, right? Or how much it tries to boost the electric field or stops the electric field. Now, this epsilon is actually a combination of the free space plus the polarization field. We learned that the materials, when they are placed inside the electric field, their internal polar structure, what we call the dipoles, they tend to align themselves into the direction of electric field. Therefore, they produces their internal electric field. That electric field is known as the polarization field. Now that field and the external field, they react and then they produce the impact of the electric field, which is actually the combined effect of both the fields. Therefore, we have D is equal to epsilon E. But if this framework is studied in, let's say, in the insulators or dielectrics, then we should use D is equal to epsilon naught, epsilon naught, epsilon R, which is actually epsilon E, right? So the relative permittivity is something that explains the how good is the material in terms of the permitting the electric field as compared to the free space, right? So In order to see this polarization effect, we understand the or we understood the impact of placing the insulators or dielectrics inside the capacitors. So, for example, if you have a capacitor, so we provide voltage, so we have a charge here, we have a charge here, right? So, if we place a dielectric in between them, so dielectric will help to produce this internal electric field. This electric field will again push more charges to deposit, right? That's what the phenomena of the capacitance help us inside the electrostatics. Now, we also we also learn from this concept that the energy stored due to this capacitor is half CV squared, right? And this formula is also equal to half epsilon E squared, right? And we also learned that the capacitance is equal to epsilon D over A, right? So the capacitance is something which is physical, right? So it's a design. So capacitance totally depends upon the selection of the design. For example, how you place the distance, how you choose the area, and how you choose the material. Epsilon is the material, D is the distance between them, and A is the area. So that actually determines the capacitance. So the capacitance help us to understand the energy. So how much energy it can store, right? So this is the whole concept of the electrostatics that we are learning in the previous chapter. Another dimension is the sigma, right? The sigma also help us to understand how good is the material in terms of the flow of the charges under the influence of electric field, right? That's what we call the conductivity, right? So we saw that different materials with different conductivities help us to grade them on the scale of the conductors such as copper, gold, aluminum. And if you look at the forces here, the force is totally due to the charges. That's electrostatic force, right? That means that when the charges, they either they attract each other or they repel each other, they will experience a force. That's called the electrostatic force. And the devices or the elements that we actually found are capacitors and resistors, right? That means that we can study this field, we can study those laws, and then we can build sensors based on the capacitance, such as the touch sensors, such as the proximity sensor, such as the humidity sensor, such as the pressure, force. So this is the concept that help us. Now, we also studied the governing equations, which are very, very important. For example, we learned that the del dot D is the charge density, right? That means the divergence of the displacement field will help us to find out that how much quantity is converging and diverging, right? So that's actually the amount of a charge. If you remember, we also look at the how the area of the curvature help us to see the charge density. That is also related to del dot D, right? So if you have a very close or very shrinkage area with a very fast curvature, the charge density will be very, very high, right? Uh, we saw that the curl of E is zero because there's no circulation. We use the Gauss's law to understand that if you know the charge density, you can find out the charge. That is the product of the area D dot ds. We also learned that E dot dl is zero for a closed path C. So that tells us that if you move from point A to B and then move from B to A, right, then the line integral is zero. Because when you move from one point to another, you have some voltage V1. If you move from B to A, then you have another voltage V2. So they are same and equal and opposite. Therefore, they cancel each other. This is something we named it as a Kirchhoff's law. Remember Kirchhoff's law? The voltage rise equal to voltage drop. But technically, E dot dl is actually voltage. We learned that if you take a line integral of electric field, actually this is voltage. But if you move back, then of course V minus V is zero. Now compare this whole concept with respect to the magnetostatics. Rather than E and D, now we have H and B, right? And they are also related to the constant. That is what we call the material, mu naught. So mu naught is the permeability of the free space. Remember, some material will help us to flow of the magnetic flux, and some material won't, right? For example, if you have a copper coil or copper wire, you can wound the copper wire on the wood and also on the steel, right? And then you can see how good is the steel in terms of the flux and how good is the wood in terms of the flux. When you apply the voltage, they both will produce electromagnet. And you would see that the magnetic field, when you use the air, is weaker, and when you use the wood is weaker. Electromagnet, same electromagnet. When you use the steel, is very, very strong. That means the materials that we use for electromagnets, they have a high permeability, right? We will discuss this. So this is the counterpart of epsilon in the Lie field. Now we have permeability. Similarly, del dot B is zero. That actually means that there is no counterpart of charge in magnetostatics, because the charges, they produce as a stationary source of electric field. But in magnetism, simple magnetostatics, we do not have anything like charge that can produce the magnetic field. Yes, we do have. That's current, not a charge, right? So that's something we learned. So H dot dl is current. That means the magnetic field intensity line integral is equal to current. But here, the line integral of E is voltage, right? That means the source of magnetic field is current here. B dot ds is zero, is not charge. That means that there is no such thing charge equivalent in the magnetic field. But the magnetic field along a closed surface is zero, right? And similarly, we have potential. We take the gradient, we get the electric field. We take a curl of a vector A, then we get a B. Another counterpart definitions in magnetostatics are the energy. Uh, as we know, the capacitors can store energy inside due to their electric field. Inductors can store energy inside the coil due to the inductors, right? So the energy is now equals to half L I squared, right? That's the inductors, what we call the inductor. Now we can have a coil, right? So the coil can help us to store the energy, right? And that's the reason if you switch off your device, usually the chargers, just like uh, your your laptop charger, if even if you switch off, you would see that the LED can still turn on, right? That's how the magnetic field can store the energy and still provide the current I, and that's due to the inductance L, right? So these are the two disciplines that we have discussed so far, and today we are going to see this part. Okay, now important thing here, just like in electric field, we have electric field due to the charges, and now we do have magnetic field force due to the moving charges. Remember, u is the moving charge, right? So the when charges move, what happens? Current flows. So the flow of current is the moving charge. So that means that any current carrying conductor, any conductor that is carrying some current will actually produce some field and also the force. Now this is very, very important. We will see many applications based on this principle. Okay. Before we start this, let's explore more about the forces here. So this is what we call the magnetic forces due to the charge. Now, uh, this is very important. If you have a magnetic field B, remember whenever there's a B written here, right, that means some permanent magnet. Okay. Let's say you have some permanent magnet you purchase from the market, like it has north and south poles, right? So, or you can have some winding, and you connect with the DC current, and then it can still act like as a magnet. So both in nature, both are same. Okay. So if you have some magnetic field, right? Let's say you have some permanent magnet and you place some conductor, and the conductor is carrying some current, right? Then that conductor and the magnetic field, they will produce some force, or the conductor will experience some force. And that force is right perpendicular to B and U. For example, if I place a magnet here, north and south pole, right? And I place the conductor here, right, in this direction, such that B and U are perpendicular. And my force would be either upward or downward, depending upon the direction of current. Correct? Right? So all the three quantities, they are perpendicular to each other. That's why we use the cross product. So the cross product means that if two quantities are 90 degree with each other, the third quantity will also be 90 with them, right? So we use the right hand rule, right? This is difficult to understand. So that means that UB, U is hitting the B, right? And the thumb is showing the force. This is one rule. This is natural rule to understand any cross product. But here you can use FBI, right? So this is basic force. I will show you in the next step. So we actually derive something better than this formula. Now, if this charges are feeling the forces, right? Remember in the previous discussion, there's also a Coulomb force, right? So charges also have forces, and the magnetic field also has a force. So sum of these two forces, Fe and Fm, is what we call the Lorentz force. Now, this is very, very important, very common, and has a lot of applications. I'll show you. So first force is due to the QE, right? Another force is the QUB. Now, this is static force. Just charges can feel the force. And this is the current. So the currents can feel the force. This is what we call the Lorentz force. Now, I'll show you what actually Lorentz force is. Check how the Lorentz force works. So that's the concept of the Lorentz force. So you see that the moving charges, they produce the force. Now, uh, let's understand this concept in more detail. The concept that we saw before can be modified into this equation. Now, this equation tells us that how a carrying conductor inside the magnetic field experiences the force. Later, I will solve some problem which is very important with respect to the exam. So it's better if you understand this properly. Now, there are three cases here. Now you would also see these kind of dots and cross in this chapter. So the cross mean into the page because current and magnetic field are perpendicular and the force is also perpendicular. So 3D dimensions are difficult to understand. Therefore, we use this type of construction. So the cross means that magnetic field is coming like this, going into the page and then coming out. Okay. So that cross means that at this position, you see the magnetic field inside. So it's inside, therefore, the current, the wire is perpendicular. So in A, there's no force. Can't use the direction of a current. Instead, we say the length of the conductor, direction of the conductor. So we use L here. Current is not a vector, right? So current is just, let's say, 5 ampere, 10 ampere. So the direction of a current flowing inside the magnetic field is done through the length. Because if you rotate the length of a conductor, the direction of a current will change. So we have reserved the concept of a current for AC value. Like for example, current either flows, the positive to negative or negative to positive. These are the only two directions. But the coil direction can be anything, right? Coil can be along with parallel, series, theta. Just like imagine coil in a motor is rotated, right? So coil move like this, right? The current cannot move like this. We only say that the direction of the coil is around bottom to top, right? Now you can use the concept of FBI, FBI, right? So that's the Fleming's left hand rule, right? So it will tell you that how the field, so this is this FB current going up. So if your current is going down, field is going up, and the F is along this direction. Okay. So that's what we call FBI rule. So if the current is down, conductor will feel the force here. So we can write the force ILB because it's a cross product. Remember, cross products are very, very interesting. That the maximum force is when this conductor is perpendicular, right? So if conductor is this way, then it's maximum. But if I move the conductor like this, and this, right? Now the field and conductor both are parallel. Then this is zero because sine zero is zero. We use the concept ILB sine theta, right? So I is current, L is the length of the conductor, and B is the magnetic field. And one more thing, if I place the conductor in a magnetic field and the close length is the force is zero, what does it mean? So it means that instead of this only wire, if I take a wire like this also inside the field, right? So if I continue one more wire here like this, then the forces are zero. Why? Because this wire inside the magnetic field will also experience the force, right? Because the current is going up, correct? And the other is going down, right? So the both forces are opposite. So they cancel each other. Understand? So that means that if you place a coil, a random coil inside the magnetic field, the force acting on the coil magnetic sum is is what? 0. One end of the coil, the sum is 0. So if the sum is 0, then how can we figure out the concept? So before we study that, we have to first look at how the inertia, so how the torque works. So for example, if you have a wheel or a simple this round shape pulley, so this is the D vector, and you make a force with F. Right now you see that F and D are perpendicular to each other. Right. So the torque is the vector D cross F. Right. So the torque is perpendicular. Now you see D is going this direction, F is going down, and T is going perpendicular. This is what we call the torque. Okay. Now this is also a cross product. Now why we study this? Because we need to understand the important concept here. So first look at this thing. Okay. So we have a construction here. So B is here. That means that let's say we have a magnet here. Okay, so the magnet is producing some magnetic field. Okay, these green lines shows the magnetic field. Okay, and then we place a coil inside, a loop inside. Okay, so loop is first going right, up, left, and down. That's how the current is moving. Okay, and there are 4 lengths. So now let's try to find out the Lorentz force on each component. Okay. If you consider the F1, which is actually on this path, right? So the current is moving down, I, and the length vector is along minus y axis, because this is your y, and then this is your minus y. Length is minus y, correct? And the value of length is b because the width is b. Cross, what is the b? B is, of course, x-axis. So b is your, okay, so b is along b naught and x-axis. Okay, so y cross x, is z, and minus plus z. So you can derive. Yeah. So this is what we call the cyclic. We learned in the cross product rule. So x cross y is equal to z. Right? Similarly, y cross z is x, and then z cross x is equal to y. So y cross x should be z because it's a reverse cycle, so it's a minus thing. Okay, so y cross x is minus y, so minus become so y cross x is minus z, and then minus become positive. Okay, now F3, look at F3 here. The current is going up, and the direction of the length is along y direction. Okay, and the magnetic field is going from minus x to x direction. So x direction. So y cross x is minus z. Now, what about the 2 and 4 part? They are 0. Yeah. Why they are 0? Because they are parallel to the field. Right? So the angle between them is 0. Sine 0 is 0. So cross product between two parallel vectors is always 0. Okay. So we have F1 and we have F3. So what is the sum of F1 and F3? 0. Right? So that means that if you place a coil inside the magnetic field, the total vector field is 0. There is no net force. How can you make it workable? How can you take benefit of that to such that it can be useful? So the idea is to create a pivot here, right? the pivot, make an axle here and use a bearings here, and let the coil to rotate, right? So what is the benefit? So the benefit is that when one force is acting up and another is acting down, it will produce a turning effect, just like this. So now our coil has some center, just like a rotor inside the motor field, right? That means that if you pull one axis down and another up, so that it will rotate, right? So that's exactly what happens inside the motor, right? So we have this type of construction now. So now we can compute the torque is equal to dF1, D3, F3, right? So you can see we can use opposite forces. These are two opposite forces where the sum are zero. Now, when you put them into the torque formula, so the D1 is minus X and D3 is plus X. So when you get multiply, you will get this value. That means that two opposite forces can be zero, but in the torque construction, if you pivot them or make a cylindrical shape to rotate or move, then it can produce a torque. And the torque is actually equal to y I A B naught. So what does it mean? So it means that the I is the current, A is the area. The larger the coil and the larger the torque, right? And B naught is the magnetic field. So there are three parameters we learned. B naught is the field magnet. If you can place a very, very strong magnet, you will get a very high torque, right? And that means you need a high current. If you can provide a high current, your torque will be high. Or the third thing is the physical design. A is the area of the loop. That means the winding, correct? So if you can make your winding larger, right, then you can have a more torque. So you may have seen that in this loop, this is useless, right? This part is useless. Therefore, you can make your loop like this, more length, such that you can increase the area. The more area you have, the more torque you have. And that's how the motor works. Okay. Now, another question. If this is the case, right, when the force is acting on this loop, right? So this is the loop, right? And then the field is acting on like this. And when the field act, the loop will move like this, right? Of course, it's rotating. If the field is trying to move the coil, and once it will move, the coil is no longer 90-degree to the field, right? That means its previous position is changed. Previously, it was 90-degree, and then when the force acting, it becomes 80, 70, 60, 40, 30, and then 0. When the loop is at 0-degree, that means in parallel, then there's no force. Then the motor should stop, right? So that's the formula. So if you look at the orientation, I'm talking about this. So if your field is like this, and then if you are rotating your coil at certain position, you see the torque becomes at theta, and then if the theta is 0, the torque is finished. Now, how to solve this problem? So you can see this one. This is the field magnet, stator. That's B naught. You can use permanent magnet or you can use electromagnet. Now, you see these coils? You see these coils? There's no single coil, right? So they are different coils. One coil is this, another is this, another is this, another is this. That means when the rotor rotates, every time there is at least one coil which is 90-degree, which plays the role of the force. If one coil is useless, another is coming. That coil becomes less effective, another is coming. So the process of force and torque keeps going on. So you see all the coils, they are placed at a certain degree with each other, right? You see, you see, at every moment, these coils are under the influence of the magnetic field. Okay, and that's how the DC motor works. So uh, in this design, there is still one issue, because when they are at the north and south, the force is strong, right? When the other side, to see the motor jerks, right? So it's not smooth. Therefore, we need to have a more winding such that the jerk between the two winding is so small, and motor starts spinning with the uniform speed. Okay, so this is what we have learned is the impact of the Lorentz force. Now, Lorentz force is quite common, and you can see one very important and simple construction. So this is very interesting. You can actually, you don't need such a complex design to just see the understanding. Actually, this wire, maybe I have better illustration. So you can see the this construction. Actually, you have a positive pole here, positive uh, point of the battery, and the current flows from here, right? And then it comes here and then comes here, right? But there's a magnet at the bottom, right? So the magnet also produces the constant magnetic field. And then because one end is going down, another going is up, so it feels again the same torque that we have discussed. One is pushing this way, another is pushing this way, and then it moves here, and the magnetic field is on the three sides, right? All the sides uniform, so it starts spinning and spinning. Now this can be there could be many crazy designs here. You see, you can place something and then it can move, right? And so people call homopolar. This is another design. This one, this one. So they all work on the same principle, that is the Lorentz force. Okay. Now let's move to some other topics. So this is the Bio-Savart law. We will go more detailed at how Lorentz force is actually produced. Now, in order to understand that, first look at this element or the conductor that is flowing the current I through its perimeter. So the length here is dl. So we are only considering the dl part. So you will see there are 2 points here. One is dot, another is cross. That means that the current is actually producing the magnetic field, right? And the field is going into here and then it's going out from here. That means it's perpendicular. Actually, it's circular. But at these 2 points, you would see that it's one point is entering, another point it's leaving. So it's circulating around the conductor. So the Bio-Savart law, they actually explain that the magnetic field intensity is directly proportional to the current, right? Now, if you want to see the direction, you have to choose the right hand rule, right? Grip rule, right? Like, so the thumb points the direction of a current, and the curl tells you the circulation of magnetic field. Okay, so if you want to see the direction, you have to use right hand grip rule. For force, we use the Fleming left hand rule. Okay, so this law tells us that the intensity is directly proportional to current and inversely proportional to r square, right? And the other two parameters are the this L and the R, right? So that means that how these two parameters are placed together. The length is placed inside the magnetic field. Now, it's important to see that previously we learned that the charges and the electric field is always perpendicular to the charges, right? So, and it's everywhere around the charge. But for magnetic field, it's not everywhere. It's only circular. That means that if you move this point to this point, there's no magnetic field. At the top, there's no magnetic field. Bottom, no magnetic field. So the magnetic field exists only this point, right? So it's close to the conductor. The circle that is very close to the conductor is strong. And when you move away, the magnetic field decreases, right? So that's how we are going to prove this. In order to understand the impact of this magnetic field through the conductor, we can use this derivation. Now, I'm not going to explain in detail, but I'll tell you that how the formulation works here. So you have a conductor and you have a small length, differential length, and we are actually measuring the magnetic field here at point P. The dl length has angle d theta, and this straight radius is r, and this hypotenuse radius is r capital. Okay, so we apply the rule here. H is equal to 1 over 4 pi L cross r over r square, and then we found that length is along z axis and the r is along this axis. So L z cross r is actually equal to phi. Okay, so we solve this coordinate system. So z cross r is phi, and then 1 over 4 pi minus L by 2 to L by 2, and then we have a L cross R sine theta because this angle is theta, right? So we have a L cross R sine theta over R square. Now, if we can solve this integral, we can actually find out the magnetic field due to long conductor. Now, there's one problem with this integral, that the differential part is only the dz, but the magnetic field is also along the other theta directions as well. So we need to convert all those parameters into the theta domain such that we can construct a triangle here. So r is this length, theta is angle, and r is this one. So we can say that r over r is 1 over sine theta. So 1 over sine theta is c as c theta. Okay, so that means that if you take r over r, that is 1 over sine theta. Z over R is cotangent theta, and dz, take just differential, is become like this. Now put all these values back into the formula and you would see that the integral becomes this sine theta, and these two can be cancelled out, and you will only get a small integral sine theta. And the integration is minus cos theta, right? So again, put back, and then you have this formula here. Now, this formula tells us that the magnetic field, sorry, H field is directly proportional to the current divided by 4 pi r, and also the difference of the angle between them. That means that how close you are going and how far you are going. You see this direction. You see like this, right? So this is your conductor and this is your point. If your point goes close, you see the theta becomes small and small. So if you go far, the theta become bigger. Now, it's also very confusing. So we convert theta into distance, right? So we can use this triangle. by apply the Pythagoras theorem and convert thetas into distance. And now plug back the values, and now you have get this information. Now, I want to again match this information with the previous discussion that we saw, the electric field of infinite sheet. We learned that if the sheet is good enough, large enough, and the point of observation is right above the sheet, we can treat as infinite. Same thing happens here, that if your point of observation, which is L, right, is is quite larger than the R, that means this radius. So let's say this is your conductor, right? This is your conductor, and then I am measuring the magnetic field here. Of course, the point where I am sensing the magnetic field is very, very close to the conductor. That means that the length is very large. Now, usually, what is this R? Now I can show you that what R actually means. So when you look at the motor here, you see this small gap, right? So this gap, and this is a magnet, okay? So that means magnetic field, this distance is the small r, right? That means that what we are trying to sense the magnetic field is almost closer, right? It doesn't make any sense to make a gap like this 3 centimeter, right? So we try to make this gap as close as possible, such that the coil moves very, very closer to the magnetic field, right? So that means that this length or this R is very, very small as compared to the length. So the length could be, let's say 6, 7, 8 centimeters. And this R could be maybe 0.1 centimeter. Okay. That's therefore we can reduce this equation into this equation. And now we have a B, which is equal to mu naught I over 2 pi R. Okay. So we can use B is equal to mu naught H. And then we have a very, very famous formula. B is equal to mu naught I over 2 pi R. So this is the magnetic field due to the current. This is the magnetic field, the impact of magnetic field due to this current, and then how you are sensing it. Now, actually, what does this tells you? This actually tells you that if you have a conductor and the current is passing through, maybe here you have a battery here, okay? Maybe it's a copper coil. Then you would see that this will create or induce the magnetic field, right? So the magnetic field will have some circles, right? So just like a ripple. So you place a stone and then there are ripples, right? So if you have a conductor, so you have a magnetic field like this, right? So that means you have a lot of circles, right? One circle is very close, another is a little far. So you have a circles that have a lot of radius. So the circle that is very close to the conductor has a very high magnetic field. Why? Because of the small radius. So if the circle become bigger, 1 over R actually reduces the B, right? That means that if your conductor is here and if you are moving away, the magnetic field is decreasing, right? And that's exactly what happens in the overhead transmission lines, right? So you have a magnetic field also. They have electric field plus they have magnetic field. So the magnetic field, the length of the pole is the height of the pole is quite high. That means 1 over 2 pi r or b mu naught I over 2 pi r, the factor is the magnetic field calculation at the ground is much less due to this r. Okay. Now, this is the formulation of magnetic field. And you can also use this kind of arrangement that we use in the magnetic field, electric field due to a sheet of a charge. You see the assignment problem. Assignment problem is also similar to this one, that actually uses the concept of the sheet and the charge sheet to find out the electric field. So we apply the same principle that we derived in previous lecture, and you would see that the magnetic field due to a long ring is equal to I over 2A. Now I want you to think about this one, that how the magnetic field along a ring is equal to current divided by 2A, where A is the grid, so that is A diameter. So the amount of the current divided by the diameter and the direction is C. Previously we saw if the conductor is straight, magnetic field is circular. Now the conductor is circular and magnetic field is straight. Inside the room, do you know what is solenoid? This one. So what's the magnetic field? Yes, exactly. So, so if you build a solenoid and put an iron inside it, right, and give the DC, it will push the iron. Power it and you put a spring and make a door valve. The force or the intensity inside the circular structure. So you see that majority of the solenoids they are built for compression purpose. And then we also make it for electromagnets. It creates electromagnets. And all types of electromagnetic waves they work on similar principles. When the current is moving, when there is overload current, the disconnection, you keep the contacts connected until you have overload. And also, you see the small PCB links. Use it to connect them. Connect the relay and then it turn on. So you can just use the connectors. When you pass the current, they connect. Just like an electric switch. Why? Okay. Why and this one? They are two different. This is solenoid. So solenoid is used to create a strong magnetic field inside. So the coil actually it's like a motor. We use a coil. That's a straight conductor. So that coil we use to have a turning effect. We make use that the force changes. We want to rotate the coil. Here the coil is stationary. We want to rotate external object. So in this, the solenoid is always stationary, and then it's either affecting or repelling another object. But in the coil-based mechanisms, the coil is moving, or either the coil is moving and trying to move another. For example, you see in the induction motor. We will discuss induction in the next chapter, so that's the electrodynamic time varying. Now we are just discussing DC. So you see that in the AC motor, the winding is on the outer side, stator. Right. And then the internal part, that the rotor, it doesn't have any winding. So that means the external winding is now producing the induction inside the rotor. The rotor does not have any sort of part because of this material of the rotor. So the rotor gets induction, and due to that current, it also has magnetic field. Then it starts rotating. because it's cheaper to build a motor without any binding on the state on the rotor. That's why AC machines are cheaper. All the fans, all the washing machine, all those stuff, cheaper stuff. Selection. DC motors, of course, we need binding on the rotor. Expensive. Takes time. They expert in that. And also it has brushes. So there are special applications. So easier to have the hole and then speed and there are another characteristics. For example, some motors we have a high torque characteristic. Some motors have high speed characteristics. That's why you see the juicers and blenders, right? We use them for high speed wave. Just like we use blowers, high speed. But for the crushing, say for the cranes, right, it's like an EVs, you use induction motor, high torque, steel motors. So it's different. Sometimes we need the speed control, position control, so we can design machine accordingly. Okay, so that's you will study the electrical machines, different subject that will teach you that how machines can be built, but the phenomena and the principles that electrical machine will use will be based on these principles that I'm teaching. The B is equal to mu naught I over 2 pi r is the fourth basic principle. For example, you provide a current and then you get a magnetic field. Now you use that magnetic field for electrodynamic purposes. Okay. Okay. So, oh, you want to take a break? Maybe take 5 minutes break and then we continue.
Yes. Yes, I mean, this additional assignment, and we have for these days for
This is
60.
different. This is different. This additional assignment, as we discussed,
This
just for practice.
just for practice.
Yeah.
No need to hand out.
No, if you want to do it, it's good. If you don't want, it's still fine. But actually, it's for those students who got less than 50 marks.
Yeah, I am.
Then you need to do it.
Submission day
16 November.
16.
Yeah.
Okay, okay.
Yeah.
And uh, and this one
This is the
this
assignment one. Yeah.
okay.
That's the continuous assessment part. Yeah.
Before 10, right?
Yes. Yeah. Yeah. Before 10.
Okay. And we have that next week, right?
Yes. Yes. Yes.
Okay. Is any like shit to see?
Yeah. Yeah. I will upload, but that's because only on the that uses because the software MATLAB, and then we will discuss during the laboratory. I will also upload the materials. So you can just download. I'll teach you how to download and then how to keep the files. So it's better we discuss when the lab starts. Okay. Okay, let's continue. So here's the field pattern comparison with the electric field. So this one is the electric dipole, which we discussed that when we have two charges separated with each other with the distance d due to the external electric field. So what we call the polarization field, and this will produce the electric field pattern like this. So it's from positive to negative. Because there's no such alternate of dipole in the magnetic field. We do not have the positive and negative charges or the replica in magnetic field. So we only have a current. So the current, when it's produced or when it's passed through a coil, it actually produces the magnetic field. But the lines of force, the north and the south poles, they can produce the magnetic field, and we can treat them as a magnetic dipole, right? The current due to the magnetic field due to the current, we can treat them as a magnetic field. Now, these field patterns, they are somehow similar to the magnetic field, electric field. The difference is that the electric field poles, they are from positive to negative, right? But the magnetic field, they are continuous poles. The field lines are continuous. In case of bar magnet, they can also be magnetic field line inside the bar magnet, but there are no field line inside the charge. Okay. This is very important topic. I will discuss this later. Okay. And let's finish the other part so we then later come to this point. So here is the electromagnet construction as we discussed before, that when we supply a voltage to a solenoid, right? So there's a cylindrical shaped wire wounding, and then you can see that the magnetic field is very strong inside the conductor. Okay. And this can be used to perform many purposes. As we discussed, it's used for the solenoid for electromagnet operations. So one possible way is also to use a horseshoe magnet type. That means that you use a coil and then you use a ferromagnetic material such as the iron cores. So the magnetic flux is now more stronger, right? So B is equal to mu H. So mu is for the magnetic field permeability of the iron or the steel. So this helps to the magnetic flux to flow from here to here, and the magnetic field within this air gap would be very, very strong. Let's say if you want to pick some iron, or if you want to have some movement inside it, or you want to provide external field to some coil, this construction would be really, really powerful. Now, let's look at the Ampere's law. Ampere's law is again the extension of the previous concept, and it tells us that if you are moving inside the a magnetic field, you take a line integral H dot dl, and you will get a current. We learned the similar relation in the electric field, that if you move along electric field, that E dot dl, you will get voltage. And then Ampere said that the current actually produces H. And if you want to find out the current, how much current, then you take the H dot dl. You take the H function and then take the line integral, and then you will get the current. But this also means one important thing, that is C. C stands for contour. So contour means that the coil or the magnetic field actually must encapsulate the current. That means that the amount of a current that you're finding should be inside the coil. And it makes sense because all the current carrying conductors can produce magnetic field around the current coil, not outside it, right? Let's say if you have a current coil here, magnetic field cannot be produced outside it, right? It should always be like this. Therefore, this case is acceptable, this case is acceptable, but this is not acceptable because the current is outside the coil, which is the contour, which is not possible. Okay. Now, if you use the same concept, so we use Biot-Savart's law as well as the Ampere's law to solve different problems in different materials and different applications for finding the electric field, current, and the magnetic field. We can apply the same concept of magnetic field along a straight conductor. and we can find out what is the magnetic field inside the conductor and above the conductor. Remember, we learned the electrostatic induction due to the inside the conductor, and we learned the Faraday's cage example. So how electric field can save someone inside the cage. And then we saw that the inside the conductor, the electric field is zero. Now see what is the magnetic field inside the conductor. So if we solve it by using the Ampere's law, we can derive this formula. H is equal to pi. Phi stands for rotational field. R1 times I. That means the current is directly, so H is directly proportional to I divided by 2 pi A square. Now we can also derive the formula for outer terminal, and we can see that H2 is also directly proportional to current divided by 2 pi R2. Now, if we plot these two results, we get this type of diagram. That means that uh, if you increase the radius, the H field is zero at a at at very starting point when the radius is zero. Soon you move away from the center point, right? You would see H increases, and then at a point equals to the radius of the conductor, the H is maximum. So that means at the corner of the material, H is maximum. And then if you leave the conductor, the magnetic field actually reduces. That means that if you want to have a impact of magnetic field, either you move a little bit above the surface or little bit inside the surface. These are the 2 points where the magnetic field is very strong. So this helps us to find out the magnetic field in the transmission media. Now, magnetic field, as we discussed before, is depend, or the intensity depends upon the choice of the materials, right? So we have an exactly replicate part of the electric field here. Remember, we discussed the permittivity for the polarization field, right? Now we discuss something, permeability for magnetic case. Now, have you wondered why your transformer is so heavy? The chargers, why they are heavy? Due to the iron core, right? But why we need iron? Yeah, because those materials, there are certain materials that actually facilitate the flux, magnetic flux, right? Due to their internal construction, due to their internal dipoles, when they are placed inside the magnetic field, right? They also have their internal magnetic field. So when they are placed inside the external magnetic field, they become magnet, right? For example, if you have iron piece and if you place magnet on its one end, you see that the iron becomes magnet itself as long as it's attached with the magnet, right? So it can attract anything else as similar to the magnet, correct? That means that without any energy inside the iron, it can still pass something, right? Let's say if you have magnet, right? And then you connect the iron piece. So here's magnet. So you can feel the magnetism here, right? Correct? That means the effect of magnetism can be transferred. That's the reason why we use the ferromagnetic materials. Now, how this works? B is mu naught H plus mu naught M. This mu naught M is the internal structure of the materials, right? And then we can take H plus M outside and mu naught inside. So this is susceptibility, magnetic susceptibility due to the internal structure. So how the molecules inside they are arranged. This is also depending upon the crystalline structure of the material, right? Now again, apply some the simplifications, mu naught H plus xm H, and take 1 plus xm, because it's difficult to work with xm, so we call it mu. So 1 plus xm multiplied by mu naught, we directly name it mu, right? And instead of solving for these complex equations, it's better to remember the permeability in terms of relative value. Let's say mu is equal to mu naught r, right? And then mu naught is for the air and mu r is for the relative. Can you guess how many times iron is stronger than air in terms of permeability? It's 2 into 10 raised to power 5. That's if you are working inside in some environment with some air, and then you replace air with the magnet. So you get 2 into 10 raised per 5 times higher magnetic field, because B is equal to mu H and B is equal to mu R mu naught H, right? Now, again, another question. Can we use copper instead of iron? We use iron, but we use we use copper. Why we use copper for let's say it's very interesting. Copper is not right. Take a magnet and that's with the copper. It's not the magnetic property. We use copper because we need some conductor that can flow current and then it can produce magnetic field. Magnetic field is not due to copper. But if you have iron conductor and then insulated that requires still it can produce. But because the conductivity of copper is good, heat losses are less. When we use material or select material high current application, look at sigma. Just look at the material activity. Right? When we choose material for electric field insulators, we look at the epsilon. Right? And so the choice of copper or iron is due to its pure copper. We have the IC and R losses are less. So per length of conductor we have some open. Then I scale R is the loss that it produces in terms. You have a good conductor, less and less I scale R loss. Right? That's to be split. Now, used to why we use iron? Need some material which is magnetic. So the flux from the conductor of the copper can be distributed from primary to secondary. That's why we use diamagnetic. This is the comparison. That is why the three types, dia, para, and ferromagnet. So there are some materials. When you put them into the magnetic field, uh, the internal polarity will be open. Let's say we have a magnetic field, right? And then if you put the diamagnetic, right, they will repel the magnetic. Very, very small. It's very small diameter. Such that it's almost equal to nothing. And they do not have a permanent magnet back. That means if you remove the magnetic field, they're lost. The example is that we don't use these for transfer of magnetic flux. Okay. Now, there are certain paramagnetism, right? They do have a magnetic moment, right? But very weak. And they can be a slightly attractive towards the magnetic field. But it's again very small. And aluminum, calcium, chromium, magnesium, uranium, palladium, these are the paramagnetic. But it does not mean that they are bad for nothing. No, that's a different story. Okay? We are only discussing their magnetic sensitivity. So sensitivity is something that comes from the internal structure of the spin of the electron. Some have a very good spin, such as magnetite remains in iron, nickel, cobalt. If you use them, they have a strong magnetized remain. That means that if you place them in the magnetic field, they spin because the electron are spinning. When they are spinning, it's something similar to currents, very small current. And we learned from the previous discussion, current produces field. So it means that they already have some magnetic field inside due to the current. And current is due to the charges, and charges due to the motion. That's called spin. No material in the iron, they have always some spin under different temperatures. But that spin is the sum of all the spins and sum of all the charges and sum of all the magnetic field is zero. Because there is no energy. But when you put them inside the magnetic field, their magnetic fields align this. Now they say, okay, we are right, what should we do? They become magnet. And then not only they become magnet, they store certain amount of magnetic, what we call stance. This is also very important. So when we compute the losses in motors and the transformer, also what happens? So when you the VH curve, so H is intensity and V is equal to mu naught H. Actually, is the relationship between B and H. If it is B is equal to mu naught H for here, the mu naught is constant. If you plot B and H for the air, you say that it's a straight line. So it's a ratio, constant, right? Now, for iron, if you increase the current and compute the H, right, and then multiply with the mu R of the iron, right, then you will get magnetic field. Right? So through the current, you compute the B. And you see that when you increase the current, right, and then you see that the magnetic field increases. It's somehow straight line. Right? But when you decrease the current, it will not follow the same path. See the arrows, it will go back to different path. That means if you make the current zero, it still has magnetic field. That means if you magnetize a iron bar, and then you remove the current, the iron bar still has some magnetic field. But if you put it on a negative direction, it reduces to zero, and then more degrees, it decreases to magnetic field in another direction. And then you increase the current into the positive direction, it will go back, and now it follows this way. That's called the hysteresis law. Different choices of different material can produce small hysteresis, but this can be here. Some material can be here, but this can be very flat. Different choices of soft material, hard materials, and it's up to you to do. So when we have motors and when we have transformers, we have losses. Heat losses, which is I square R losses, which is resistance. And then we have hysteresis losses. Hysteresis losses due to linear being used inside the motor transformer. So this is very interesting property, very different from the E fields. Okay. So this is our inductor design. So we can actually design some sensors based on the magnetic field. So you would see that we have plenty of sensors available that actually make use of the concept of magnetic field to translate one property into another. For example, motion or force or displacement. We use this linear variable differential transformer. So transformer mean because it works on the principle of induction. Linear stands for the straight line connectivity. Now, consider this arrangement. So this is primary coil. So we give him AC. This is AC value, right? And this is ferromagnetic core. Remember, the purpose of the core is to supply or transfer or flow the magnetic flux from one end to another. It provides a connection of magnetic linkage, right? And another good thing, they are not connected electrically. There's no electrical connection. Remember, you know that, right? When you see the transformer winding, primary winding is done on the iron core, but there is no short circuit, right? So the winding is already have the insulation. And then on insulation, we also have papers. So it's totally electrically isolated from the iron. Remember, this is a very important point. So the only connection is magnetic. They are magnetically coupled because the primary is giving flux to the core, no electrical connectivity, right? So there's a gap here. You see, there's always a gap. And then iron. Iron has a very good mu R. So it takes the flux from here, it become magnet. Whatever changes in the primary, iron also do like this, right? If the input is changing sinusoidally, iron is also behaving sinusoidally. Okay, it's like a magnet now. Now, there are certain coils here under the influence of iron. Okay, now if this iron moves here, you see now this coil is under the full influence, but this coil will be alone. There's no overlapping of the iron on this coil, correct? Now, remember, this is like a transformer, right? So this is primary, this is secondary. There are two secondary coils. But the connection of secondary is reverse. You see, direction is reverse. So that means that if V1 is here, minus V1 is here, right? Or minus V2 is here. So that means that if it moves on this way, right? So there, this voltage will increase and this voltage will decrease, right? So there's a difference between them. That's why we can use the term differential. So there's a difference in two coils, and that difference will appear here. Okay. Now, if it goes back, suddenly we have same difference here, but the polarity changes. Now, if you translate the motion left right into voltage, you would get these curves. For example, if you move on another way, you see it linearly increases. The voltage linearly increases. Now you can use here to microcontroller, and then you can sample the voltage and convert into some digital value. That means that shows you the amount of force in newtons or probably the displacement. Let's say millimeter, centimeter, whatever you like, right? So maybe 1 millimeter movement is equal to 1 volt. right? And then number of volts multiplied by the distance, you will get the final answer. Now, if it is moving on this way, you see the voltage increases, right? Let's say 0.5 volt to 5 volt, right? And then if you move another way, like it also increases, right? And at the center, it's zero. So you can see that any meter, any reading on the meter will actually give you the voltages, right? That's what we call the displacement, right? Sub-millimeter precision. So a slight movement can indicate the difference in voltage, right? So that's how we can create a sensor. Another important application is the eddy currents, right? So I talk about two losses. One is high speed R losses. We also use the as a benefit meter high speed R. But these are the devices. But in normal transmission line and high speed R. Another loss is the that's a third loss is eddy current loss. Now, I'm saying losses, but it's also a blessing, also used as a blessing. For example, this is the primary coil. And we find these, and it's just like it comes from output. We have output that's 5, 6, 10, whatever. Now, this is exposed. This is my area is exposed. That means that you place something near to it, and it must. I have an iron piece. Closer, magnetic flux is not the iron piece. Because it's an AC. Change in magnetic field will produce and current. That current will then this current and this, and therefore if the voltage decreases, let's say that voltage happen near. Then finally what we do, since we learn for the metals we magnetic current. Then actually there is a coil. Coil is looking for matter. Whenever it finds the matter, the induction stops and the voltage falls. That's just peak in the voltage can be really done with the is the actually effective due to eddy currents. This is the blessing of eddy. Another blessing is the eddy current have a diamond, then we have a disc. This thing. Then if you increase the magnetic field, this is moving. Then the chain will use the voltage and the current. Then it will try to stop by the Lenz's law. Again, oppose the magnetic field and try to stop itself. That's how you can create a breaking without potential eddy current breaking. Eddy current breaking. Okay. So this is your eddy current breaking. You see? Non-contact breaking. Okay. Now, eddy current. right? So this is a coil. Okay. So the coil is fluctuating. I mean, we will study this in next chapter because this is time varying magnetic field. And this will produce eddy currents because now you see this is also a conductor. Same happens in metal detectors. So this metal when comes here, it it actually gets eddy currents and to detect the change in voltage. Now there's a magnetic field, and then this produces the current, and then the current produces heat, and then heat can help you to boil something. Okay. Same thing. Induction. We will study this by Faraday's law of electromagnetic induction, time varying field. That's our last chapter, last question, last topic. Okay. It's clear? Okay. In vehicle,
I mean, the braking system you just talk about.
a braking system. Yeah, yeah.
I Sheheryar or
Yeah, of course, in trains.
oh,
In trains. You see, these are the trains, locomotives. You see? Or not only trains, but you can use it industry anywhere. So let's say you don't want thing to be friction detect. You need a direction on that. And then again, they are eddy current. Maybe the different supply actually eddy current. So eddy current has different benefits and different disadvantages. This is the benefit. But in motor, we don't want it. In motor, we also have eddy current. Right? Because when we use a motor, right, and when it's induction, produces magnetic field, but it also has currents. That current pass through the material of the road, and then that current will have high scalar losses, and then we have to pay for it. We don't in motor, we actually don't want any current. Yeah. So what we do is yeah, you see we have so actually we use these kind of laminated discs here. You see, so it's not a complete conductor. So we have a very small conductors, and then we put them into the lamination such that we do have magnetic flux, but we break the path of the current. So I square R losses are minimized. Right. So we use discs, a simple disc laminations. Right. There are many ways. See, there are different constructions here. So we use lamination. So it's better to break the path of a conductor into different lamination sections. So then there's no current. If there is a current that still remains in the simple disk, does not travel, and then I square R losses are minimized, right? So we will also study this in our next lecture. But now let's come to the most important topic of today's discussion. Okay, so this is very important in terms of exam point of view. So the problem is we are asked to- okay, we use the concept uh, of the the force due to the current carrying conductor and find out the whether the forces are attractive, repulsive, or what is the force. Okay, so remember, you can use these two formulas. First formula will give you the magnetic field due to the current, and the second formula will give you the force due to magnetic field. Understand? So the first formula is very simple. We learned this mu naught I 2 pi r. Okay, we learned this. Correct? Now, this field means phi naught. Phi naught is like this. Okay, right? We learned this. The field is rotational. Now, here we have two conductors. Okay. It's producing magnetic field. Now, field is going this. Right. Only this part of the field is interacted by this conductor. Okay. So you see the field is actually going down at the conductor. So it's going this way. So it's going this way. So it's minus x. That's why we have minus x. When the field cuts this conductor, it goes down. Understand? Current is I1. Remember, this field, green, belongs to this one. So the direction is minus x, and the field is due to I1 2 pi d, because this is the d distance of conductor from the magnetic field. So this is r, right? R. This is the radius of the circle of the magnetic. Is this clear? That's how you can find out the magnetic field due to the conductor. Okay. Now, second one, we have to compute the force due to this current carrying conductor, and the field is this one. Now, remove everything and just consider you have a field. Right? So, this current is moving up, and we have to find out F2. F is equal to ILB. That's what we learned. So this current, this force is I2. What is the length? Length is along z-axis. Z-axis. And cross B. B is this one. So this green is the B. Okay. So put this B here. Now, C cross X is equal to Y, and minus comes here. That means the force is along y-axis. So where's your y-axis? Thus, this is negative y, so we consider this one. Okay. By using these unit vectors, we can solve. So x, so this z cross x is y, and this y is. So you have to practice it many, many times to understand that this B is due to this conductor. This is primary conductor. it's producing magnetic. So if you want to compute force on conductor I2, right? So you use the current of I2 and use the field of the primary source. So as I mentioned, this question is very important with respect to that. Don't ignore it. Mu naught I1, I2, L, 2 by D and minus 1. Okay. Now, this is just force per length, and just forget about this. This is just because both have the same length, so we can put L on the downside, 4 per length. But maybe in exam, you're given 2 centimeter, 2 meter, whatever. You can put the value 3 ampere, 5 ampere, 5 distance is 3 centimeters, then you can find the force. Okay, now this is F2. How about F1? Sorry, opposite way? Yes, yes, yes. So this current is going up, right? So its field is like this. So its field is now going into X direction. Okay, like this. Field is going like this. This one is like this. Its field is going like this. Its field is going like this. Now you can solve for F1 and you will see that it's again exactly the same value, but the value of unit factor is 5. That means going this way. So if one force is going here, another force is going here, it means attraction. Yeah. No. This is moving this way. And this is moving here. Then attracted or repelled. If the two come closer, that's attraction. So you get attraction. So if both currents are going down, is attraction. If one is going up, one is going down, then repulsion. Okay? Okay? So you need to solve this for understanding. So if there are two parallel wires, they will attract if they are in same direction and repel if currents are in opposite direction. Okay? This is very, very important. Any question? So if you consider this I2 going down, right? Then length of I2 that is going down is minus Z. Right? So only change is this one because I1 is still going up, therefore no change here. And then it will become positive Y, right? And the other force is still in the same direction. Okay. That means that now both are moving along y direction. So they will repel. One goes right and another also goes right. So they will repel. Okay. So you can now think about these two relationships and then try to solve the. Okay. So this chapter, we will only include these topics, and there's one complete question from this chapter. Okay. So we may ask you some question related to the sensors. Let's say what is LVDT, what is, let's say, eddy current, what is eddy braking, or maybe what is magnetic field of a wire, something like that. Okay. Maybe some problem. Okay. Force, what is the force due to the current carrying conductor, or compute the force, whether they are attracting, repelling, maybe three conductors, maybe four conductors. Okay. Okay. Didn't understand? Any question? No? Yeah. It's okay. We will also do some practice in our last lecture to solve some problems also. Yes, sure, sure. We will show you. One more. So far, three questions. So far, we have finished three questions. One more question. Okay. So if no more question, we can finish here. So as you can see, we have also uploaded the assignment, additional assignment. Okay. It doesn't matter whether your marks are above 50 or below 50. You should try